Good morning, guys. Today we're going to go over Chapter 4 of Physics 101, Motion in Two Dimensions. So, in Chapter 2, we started discussing motion, right? And for the most part, we were discussing it in one dimension, which is basically, say we're considering the distance, we're considering the position of a car driving. Well then, in that case, pretty much considering it only along one axis, which would be the x-axis, right? However, it's important that we also consider the y-axis, maybe not for a car, but for a particle. Say, in the case where, say we want to consider two dimensions, right? Well, we're going to want to know where a particle is in two dimensions instead of one dimension. And in this attempt to pinpoint the position of a particle in two dimensions, we're going to use the vector r, which is the position vector in two dimensions. Position vector in two dimensions. All right, and so if we were using a scaled x-axis and y-axis, so like this, bang, bang, bang. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here we have 3, 3, 3, 3. 1, 2, 3, 4, 5. And then the y-axis title is over here. So in this case, we are again discussing position. However, it's important to note that the position, or the way that we evaluate position, is no longer going to be in one dimension, but in two dimensions. And the way that we're going to do that is with vectors, what we learned in Chapter 3. So you see, we can, instead of just claiming this to be coordinate 2, 3, we're actually going to use the r vector to pinpoint where, pinpoint the distance, pinpoint the vector that separates the origin from that very point, right? And so if we call this R1, it would have the components of 2, 3, right? And that's pretty much it. And if we were to consider yet like another point, let's call it maybe like 4, 8. This would be R2. We call it 4, 8, or actually 8, 4, my bad. 8, 4. And then we're going to move this a little bit so that we have a more clear image. This is 2, 3. All right, now we have 2 points, right? 2 positions of the same particle in a given situation. We don't know at what time they're at these different positions. However, what we do know is that they are at these 2 different positions at 2 different given times. And if we wanted to finally know the displacement, which we had defined before as delta x, then we would actually have to do delta r, right? The delta of the change of the r vector, right? And so what we'd be doing is r final minus r initial. And so our final in this situation would be R2 because it's the second one and R1 would be the first. So if you remember anything from chapter 3, we would actually be doing a arithmetic operation of vectors here. We'd be taking this vector and we'd be subtracting it that one. Or we'd be adding the scalar opposite, or like if we multiplied this vector by -1, then we would be adding that vector to this one. Otherwise, the way that we would calculate this is by taking the two vectors, putting them tail to tail, which we've already done, and then taking the first one, right? Going from the second one, that one, to this one, from R1 to R2. We're just going to trace a line. And this is basically that vector, the displacement, right? And if you think about it, the vector, we can also calculate it algebraically. I always have trouble with that word. We can calculate it. It would be this minus that. 8 minus 2 is 6. 4 minus 3 is 1. Therefore, we have 6, 1, right? And yeah, that's pretty much it. The only other mention I would like to make is that we can often, even though we don't have any time associated with these two positions, we can just mention it on the side. We can say at t equals 5, and we can say at t equals 2. And that way we have an idea of at what time these vectors are at these points. We know at what points in time these particles are at these different positions, right? So it's worth noting that the displacement is the shortest path. The shortest path between a particle's final position, between a particle's final position and its initial position. All right, that's pretty important. And it's also independent of the coordinate system. And what does that mean? That actually means that regardless of what these vectors, regardless of where the coordinate system was, we would always have a displacement of 6, 1 for these two specific vectors, right? Yeah, exactly. That's pretty much it. A vector is basically self-defining, right? It does not require a coordinate system to be defined, right? So this vector R1 has 2 as an x component and 3 as a y component, and that would be the case even if the vector, even if the coordinate system was like over here, it would still have those components, and its angle would still be the same, its magnitude would still be the same. And that is the reason that displacement is independent of the coordinates of the coordinate system. All right. Now, this is great and all, but the main purpose of talking about motion in 2 dimensions is to do what we like to call decomposition of motion. And we're going to do so much of this. Decomposition of motion. Basically, what we'll be doing is breaking down a velocity, for example, or an acceleration in terms of y and in terms of x, the two axes of the two dimensions that we're talking about. So motion in 2 dimensions can be modeled as 2 independent motions in each of the 2 perpendicular directions associated with the x and y axes. That means that any influence in the y direction does not affect the motion in the x direction and vice versa. So we're going to write that down. Any influence from the x direction does not affect the y direction and vice versa. Any influence from the x direction in the x direction does not affect the motion in the y direction and vice versa. This is a very, very important concept that we're going to have to wrap our heads around. Viewing 2-dimensional motion as 2 separate motions, one along the x-axis and another along the y-axis, is referred to as decomposition of motion, like what I was saying. So we're going to consider 2 independent motions along x direction and along the y direction. Okay, well that's fantastic. Great. So basically, if we were to redefine velocity, position, and acceleration, it would be like this. Now that now that we can basically decompose each of those aspects of motion, now that we can decompose them in terms of x and in terms of y, we're gonna have a couple of new formulas. Not really, actually. If you think about it, you don't have to memorize these formulas. They'll come to your mind immediately. As we were working before, the x, so this is position, right? I'm gonna write it over here. Position is r equal to x, comma, y, right? Then we have velocity, which is v is equal to dr, right? I'm sorry, delta v is equal to dr dt, right? But it's important to decompose this very same motion into other ones, right? So we have v of x is equal to dx over dt, and v of y is equal to dy over dt. The same goes for the average accelerations and the average velocities. I'm going to write that over here. Average velocity in x is actually delta x. Average is equal to delta r over dt. So we have that, not dt, delta t, and we have delta t here. V average of y is equal to delta y over delta t, right? And the same goes for acceleration. We have a is equal to dv over dt, right? And we can rewrite that as a of x is equal to dvx, right? dvx over dt, comma, ay is equal to dvy over dt. Perfect. So, and we can also do that finally with average acceleration, which is delta v over delta t. A average x is equal to delta v x over delta t, and average y is can be equal to delta vy over delta t. And that's it. We now have a whole new set of equations, right? And you don't have to memorize these, you just have to be aware that we're gonna have to decompose velocity, acceleration, and position into x and y. And that's pretty much it. Yeah. So speed is the magnitude. Yeah, so it's also worth noting that speed is the magnitude of velocity. So in this situation, this is how we would evaluate speed. All right, always using Pythagorean's theorem. Next, instantaneous velocity vector is always tangent to the path of the object. That's also another good point, right? So what that is saying is, say you had a path, like a car was driving along this path, like literally. Bang, 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 bang. It's a little ugly, but work with me. It'll work. We have a car moving along a path. At every given tangent, the instantaneous velocity is always going to be tangent to the path of the object. So this is instantaneous velocity, right? At this point, exactly. And the same, and over here, we're gonna have something like this. And that's pretty much it. Finally, we're going to go over something that we might have had to go over a little sooner, but is quite important, right? It's all right that we're going over it right now. It's just something it's like a visualization of speed, velocity and acceleration. Yeah. Velocity and acceleration. Okay. So basically, we're gonna have 4 cases, right? We say we have a car. Okay. And imagine that the motion is in the positive direction, right? So we're heading in this direction. The motion is basically the velocity, like that, and is speeding up, right? If it's speeding up, then we know, oh, wait, I believe I made a mistake in my notes. I should change that actually, really quick. Sorry for the wait, guys. Yeah. A very small error, worth changing though. Alright, so if the motion is in the positive direction and the car is speeding up, then we know that both the acceleration and the velocity are going to be pointing in the positive direction, and they're both going to be positive, of course. That's what's going to lead the car to accelerate. Now, if we have motion in the positive direction, and the car is slowing down, then we have a slightly different scenario. Okay, so we have v of x and a of x. So in this situation, the velocity is going to be positive. However, the acceleration is going to be negative. It's going to be fighting against the already positive motion direction of the motion, right? And as a result, it will slow down the car. Okay, and so we're going to see a very similar situation when the car is moving in a negative direction. And this is going to show us just how much the coordinate system that we established is going to dictate everything. So in this scenario, so here the car is always going like that. Now we're going to have a car that's going in the negative direction. So the velocity is going to be negative, and the acceleration is going to be negative. However, it's still speeding up. The speed is increasing, right? The speed, meaning the magnitude of that velocity, is increasing, though it's becoming more and more negative, right? And if we think about it, if we have motion in the negative direction and is slowing down, and the car is slowing down, well then our intuition at this point should pretty much tell us that the acceleration and the velocity vectors are going to be in opposite directions. The acceleration is going to be positive, the velocity is going to be negative. And that's pretty much it. They're fighting against each other, therefore the car is going to be slowing down, right? The already negative speed, then already negative, negative motion, the velocity, is going to be slowed, is going to be reduced as a result of the acceleration being positive, pointing in the opposite direction. And this is a very good intuition to have in physics, and I really recommend you guys study this a little bit, implement it into your heads, just implement it into your work. Just make sure that you have this very, very good intuition. It's also very, very satisfying to be able to just come to these conclusions pretty quickly, right? And what is next? I think that the one thing that we're going to do next is a practice problem. And we're actually going to be we're going to be using one specific idea that was mentioned not too long ago, right? Say we have a car that is traveling, a car is traveling on a hill at a constant speed of 10 meters per second. The topography, meaning how bumpy the road is, topography of the road can be described by the function y of x is equal to negative 0.005 x squared plus 50. What are the Cartesian coordinates or components of the car's velocity vector when x equals 40? Okay, so this seems like a very odd problem, right? A car is traveling on a hill at a constant speed of 10 meters per second. The topography of the road can be described by the function y of x is equal to negative 0.05 x squared plus 50. What are the Cartesian components of the car's velocity vector when x equals 40? Interesting. If we look back a little bit, I had not very long ago said that the instantaneous velocity vector is always tangent to the path of the object, right? So this function defines the topography of the road, which is basically the path of the object, right? It's going to be going up and down and up and down, up and down. And if we find the derivative of this, we would actually be finding the value of the slope at every single point along this line. So let's go ahead and find that. So we do that, it's 0.01 x plus 50, which is no longer there because it just gets eliminated, it disappears. Is that correct? I believe it is correct, right? And now, if we just plug in 40, what does that number mean? What do we get? Negative 0.4. What does that mean to us though? This actually is the value, I'm sorry. Yeah, with this value, what we can do is actually draw out this. We basically have the slope of the topography at x equals 40, right? So basically what we have is an angle over here, and because it's negative 0.4, we know that for every 1 meter, or at least for every 1 unit in this direction, we have negative 0.4 in this direction. And with this, we're actually able to find the angle that basically, the angle that breaks down the x and y components for the velocity at that point, right? So if we use the tangent, the arctangent, we're able to find the angle. We put negative 0.4 on top, here, put that, and what we get is actually about negative 21.801 degrees, right? And so at this point, what do we have? We know what the actual, we know what the magnitude of the velocity is. So what we have, if we call the velocity delta v, the vector v, then what we have is 10 comma negative 21 degrees, or negative 21.801 degrees, right? And now what we want to do is find the x and y components. Right. And so the way that we're going to do that is using the conversion methods that I taught you guys a little while ago, in the last video actually, in chapter 3. So we have the magnitude, we have this, so we just do 10 in order to find the y component. We do 10 times sine of negative 21.801 degrees is equal to, and for the x component we do the same but with cosine of 21.801 degrees, and what do we get? We get negative 3.714 meters per second, and we get 9.285 meters per second. And with that, we have our answer. And there you go. That's the answer to the question. The question was asking for the Cartesian components of a car's velocity vector when x is equal to 40, which is this. And that's it. We have the answer to our question. All right. I believe that is enough for today's video. We will continue shortly with projectile motion in the next video. Thank you so much for watching, and I'll see you guys in the next one. Bye.